Hello students, in this video we'll discuss about Turing machines. So in the last video we have discussed the decision properties of context-free languages. So that is from the third unit. Let me go with this. First, Turing machines, where we use actually and where it is. See, the regular languages are accepted by the finite automators, and context languages are PDS, and Turing machine are going to recognize the Turing recognizable languages. So, of course, there are some languages which are not context languages. Those are going to be recognized by the Turing machines. And we can say that the Turing machine can accept all the languages like regular, CFL, and Turing recognizer, recursive enumerable languages. So first, who developed the Turing machine? The one who developed the Turing machine is Alan Turing, right? And we have a Turing Award also on his name because of his excellence in developing the computational device like Turing machines. So, which is a more powerful model than any other machine existed, right? And of course, it is a more accurate model of the general purpose computer. And we can say that whatever the tasks done by the Turing machine, I mean, say that computer, all can be done by the Turing machine, right? So even a Turing machine cannot solve some certain problems. Of course, those problems are called as undecidable problems that we'll discuss. And what is the model of Turing machine? See, in all the remaining automatas, the models are also same. Like it is going to have the infinite tape, but in this case, the tape is rewritable tape. We can read it and we can write it. And the head. So as of now, in PDA and finite data meta, the tape was only readable, but here it is rewritable. And the head was moving only one direction in the earlier machines, but now it moves in both the directions, left to right and right to left. So then we'll be having, so the tape would be infinite length. Sometimes it is open both sides, sometimes it is open one time. We have some types of machines that we'll discuss later. So if you want memory, for example, the finite data method does not have any memory, but when it comes to the PDA, we have a stack memory. And we can say that, see, the finite data meta with zero stack, we don't have any memory. And PDA means finite data meta with one stack. So that we can call it as push down automata, right? And finite automata with n stacks, infinite number of stacks, would be treated as Turing machine, right? So if you want memory as like stack or queue or whatever it is, right? Just go to this and utilize the space here and here because the tape is infinite length and rewritable. You can read it and you can write it. Then how it is going to perform the computation? See, first read write head starts at leftmost position on the tape, and input string written in the in blank here, the square, and end of the input string is denoted with the blank symbols. In some textbooks it is denoted with the right cross blank B, or sometimes it is denoted with the delta. So of course sometimes it is denoted with the cross C, but they'll tell you how it is going to be, right? So then the Turing machine computation would be like this. So on a state, if you read a particular input symbol like A, then it will tell you what would be the next state, and whether you are changing the input symbol or you are keeping as it is. For example, I am changing A to X, then you can write it. So this is updated state symbol and in which direction you are moving. So that is the computation of Turing machine. That's what we are saying. We have to tell on a particular current state if here an input symbol is read. So this is the current state and this is the input symbol. And a particular state if you read a particular input symbol, and what is the next state we are going, and whether you are updating the tape symbol or you are keeping it as it is. After updating, where you are moving, the direction. So the direction can be either it could be right direction or it could be left direction. Sometimes it would be no direction. Means the tape, the head don't move anywhere, right? The head doesn't move anywhere. It keeps in the same position. The computation ends if when it enters either the accept or the reject state, right? So then what is the tuple notation of Turing machine? Of course, again it is a 7 tuple. Q denotes a set of states, of course finite, definitely. And sigma is the input alphabet and not containing the blank symbol. So sigma doesn't have the blank symbol here, right? So the blank symbol is separately denoted by the machine. And the toe is the tape alphabet, like stack alphabet. We are going to have the tape alphabet, where the tape alphabet blank symbol is belongs to toe, right? And of course, sometimes even the input alphabet is also a subset of tape alphabet, because initially we are going to have the input symbol on the tape, right? So definitely whatever the symbols we are using here, that also comes under tape alphabet. And we have, other than input alphabet, we have some other symbols, like if you are updating into something, right? Then just we have discussed earlier, and this is a current state. And if you read any tape symbol, right, it includes the input symbols also. Then what is the next state and what is the updated symbol and which direction you are moving. So same thing, whatever we have discussed in the earlier slide. So that will be denoted as a transition function. And of course, Q naught is the starting state, must be only one. And Q accept is the accepting state, and Q reject is the rejecting state. Most of the cases, right, not most, always the reject state must not be equivalent to accept state, right? Then we have a hypothesis. What does it mean by hypothesis? Let me go with this. See, guys, as I told you, the most powerful machine is the Turing machine. Most powerful computational device is Turing machine, which was developed by Alan Turing, as I told you. That is a English computer scientist, mathematician, logician, right, and philosopher and theoretical biologist, like, of course. So he has done so much research and so much work in computational devices, right? So that's what I told you now. Based on his work, right, or research done in the computational device, so we have an award also. So the one who is doing excellent work in computer science department and computational, so they will be honored with the Turing Award, right? So then what he is doing, right? The one who developed the first computational device, right? Alan Turing, right? And every language, every problem which is accepted by the Turing machine can also be done with the computer, right? So we can say that the expressive power of a Turing machine is equivalent to the expressive compute power of a computer. Means the power of Turing machine and computer are both are same, right? According to that, the earlier slide we have discussed, even the Turing machine is much accurate than the general purpose computer, not the supercomputers or something like that. So general, what are the computers we are using? Even the Turing machine is more accurate than that, right? So then what is this hypothesis, right? See, if a problem is solvable by the computer, then also it is solvable by the Turing machine. Or if a problem is solvable with the computer, then also it is solvable with the Turing machine. And vice versa, sorry, vice versa, right? Then, for example, you can't give any problem which is only solvable by the Turing machine but not by the computer. Or you cannot give any problem which is only solvable by the computer but not by the Turing machine. That's why we are saying that both are equal power. And what does it mean by this hypothesis? See, here we have two statements. Like you might have in your childhood, you might have listened this hypothetical questions like which is first, hen or egg, right? Everyone is having their own explanation to prove that their perception is correct, but no one proved that the other one is wrong. So still it is a hypothetical question. So they are having the supporting statements to prove that their statement is correct, but don't have any explanation to prove that other one is wrong. So that means hypothetical question. Same here, what is this Turing and Church hypothesis? Here, see, the Turing is saying that a problem P is solvable by the Turing machine. A problem P is solvable by the Turing machine if and only if it is solvable by the computer. Right? That's what the Turing Church is saying. Alonzo Church is saying that, see, a problem P is solvable by the Turing machine. Your Turing machine is saying to the Turing that your machine can solve the problems if and only if the computer can able to solve it. If computer can't solve it, your machine can't do it. But what Church is saying that a problem P is solvable by the computer if and only if it is solvable by the Turing machine. I can say that no problem which is solvable by the computer but not by the Turing machine. There is no. So I can say that both are correct. Everyone is having their own proofs to support their statement, but none is having the statements to prove that the other one is wrong. That's why still it is an hypothetical situation, right? So then in the next concept, we'll discuss how to construct the Turing machine for a language.